So in this video, we're going to talk about the coordinate systems in R3. We've already discussed rectangular. We're going to introduce two new ones now, cylindrical and spherical. Now remember, we're in R3 when we talk about this. So for rectangular, just kind of as a review, our ordered triples would be in the form X, Y, and Z, and we know how to map out those points. Cylindrical now, that's going to be essentially your polar coordinates, but in R3. So the order triple is going to be r, theta, and then we're going to have this z component. If you'll remember, r is always defined as bigger or equals 0, and that theta is always going to be defined as between 0 and 2 pi. The only additional part now is the z, which happens to be the same z as that was. I'll draw this out for you in a picture in just a moment. Spherical is one that's going to be a little different. The order triple is going to be the Greek letter rho, the Greek letter phi, and then we have our theta. That rho is going to be bigger or equals 0. The phi is going to be between 0 and pi. And then that theta is also going to be then the same as it was for cylindrical, between 0 and 2 pi. So this is just kind of a summary and overall view of what it is we're going to be dealing with. But I'm going to go ahead and draw these two out for you so you can see exactly where this stuff comes from. Okay, so I've got on the screen now the XYZ space in R3, and we're going to study the cylindrical coordinates. And so to get this started, what I'm going to do is actually draw a triangle back in the XY plane. And so that triangle right there is going to give me my right angle. So if you ignore the z-axis and you just view the xy plane, that's just your typical triangle that I would normally draw in the first quadrant of the xy plane. So since cylindrical is just an extension of polar, it probably is going to be obvious to point out that this guy right here would be our theta, and then this guy here would be our r. So we would move out a distance of r, we'd move around theta, and then that would put us at this point right here. Now, the other component now, since we're in R3, would be the z coordinate. So let's say I move up, and I'm sitting at this point right here. That green distance, that would be your z. So really, the only difference is now we have a vertical component tacked on to that order triple. So this point that I have drawn, this would be the XY Z point. It would also be the R theta Z point. I want to go ahead also and make the connection similar to what I've done in polar back in Calc 2. We know that if looking at this picture here, we know that x equals r cosine theta. We also know that y equals r sine theta. And then z would just be itself. Like I pointed out before, that z and that z are the same thing, so z would equal itself. We could also carry it on a little bit further and say that r equals the square root of x squared plus y squared, and that tangent of theta is going to be the y over x. None of this information is new to you, but it is going to be important when it comes to converting from one coordinate system to another, and so it's definitely worth pointing out more of as a review than anything at this point. But cylindrical coordinates, again, pretty straightforward, assuming you have a good handle on polar. All right, so as we discuss spherical now, this one's going to be very different from what we've seen in the past. So what I'll do is I'll start out with a point. Let me just start off with this point right here, and I'll go ahead and bring out this distance right here. I'm going to also drop down a certain distance, and then I'll come out from there and over. Now, again, it's difficult to draw this type of stuff on a two-dimensional screen, but what we're doing here is we're actually creating a right angle right there. So this is going to be our right angle. This is essentially going to be our hypotenuse. And so this point that we're focusing in on, I'm going to go ahead and to start, I'm going to label this point right here, both r theta z and rho, phi, and theta. The reason I'm labeling both is so you can see the connections that we're going to need to make here in a moment. But now, in terms of the rho, the phi, and the theta, the rho, the phi, and the theta. Rho, if we're considering this point, rho is going to be this distance right here. So that's going to be our rho. Our theta is going to be the same theta that you saw up here. That was our angle from here around. So this guy right here would be our theta. And the phi, that's the one that's going to be most interesting. The phi is actually going to be the angle that we take from the z-axis, starting right here. Picture a ray, if you will, starting here with its initial point, coming up, and that thing's going to drop down. As it drops down, that's going to give us our angular measure. Remember, phi was defined between 0 and pi. So from here all the way down to here is where it's going to be defined. So for our picture, the angle from here down is going to be our angle phi. Okay, so we'll talk about this when we get into more pictures as well, but just remember the rho, the phi starts here and drops down, and then the theta comes around as it would have for cylindrical coordinates. Now, to put some things together here, the first is going to be a little bit of geometry. If this angle right here is phi, then this angle right here would also be phi, assuming that these two lines are parallel. So I'm going to go ahead and mark that as phi as well. Make that a little bit bigger and easier to see. And then from here, we can go ahead and make sure that everybody's clear that this could be our z, if we're r theta z. So that could be our z. And then this would, of course, be our r. That guy would be r. So I've labeled this point two different ways, r theta z from cylindrical, and then rho phi theta, rho phi theta for those. So the connections, again, are going to be what's really important to make here. So I'm going to start by studying this angle right here. So cosine of this would be our z over the rho. So cosine of phi would be the z over the rho, which would mean that z equals rho cosine phi. That's an important one to remember. Similarly, sine of phi would be the r over rho. So r over rho, which means that r equals rho sine phi. Continuing down, the tangent of phi would be an r over z, and I'll just leave that one sit as is. We also know that rho could equal the square root of r squared plus z squared. So rho could equal the square root of r squared plus z squared, which actually, since we know what r is from cylindrical coordinates, that's going to actually give us the square root of x squared plus y squared plus z squared. So we've got four really big connections here, and you know what, I'll make it five. I'll even say theta equals theta, much like I said z equals z in the last screen. Because if we're really talking about how these two coordinate systems interact with each other, again, that theta is the same as that theta. So theta equals theta is another observation we can make. So these five things are going to be really, really important in converting from one coordinate system to another. The other thing that I need to point out, which is going to be really important, is if you'll remember, we know that x equals r cosine theta, and we know that y equals r sine theta back in polar and cylindrical coordinates. But now, since our r is equal to rho sine phi, I can take this now and substitute it here and here. This is going to now give us x equals rho sine phi cosine theta, and a y would equal rho sine phi sine theta. So two more connections that can be made bouncing around from coordinate systems. And again, it might seem like this is all kind of trivial at this point, but when it comes to working with these integrals and converting coordinate systems, all of this information is going to be helpful to make this to make sure we're dependent upon the correct variables.